Hello everyone, let's continue our discussion in the TCP congestion control. Our goal for today or in this video is to understand how the TCP implementation works, especially in the TCP Tahoe and TCP Reno. Alright, so let's go to the concept. We have seen this figure previously, but let's repeat what we have studied before. So here we have the green segment, uh, which is a segment that was already sent, and the sender already received the ACK from this segment. And then let's say the congestion window is the yellow and the blue segments. This means that the sender can send the segments up to this many bytes, okay, in the congestion window. But then it only sends this yellow segment, and there are still several bytes that can be sent uh, it, in the blue segment. All right, so we can define the congestion window as the last byte sent minus the last byte X. So this is the maximum congestion window. I mean, this is the maximum bytes that can be sent by the sender. So it shouldn't exceed the congestion window. I mean, if we also combine with the flow control, this will be the minimum. Okay, the minimum within the congestion window and the flow between the congestion window and receive window of the receiver. And this congestion window is dynamically adjusted in response to observed network congestion. So, and how we get this information from the network congestion is from the timeout and triple duplicate ACK. And this will be different from one TCP implementation to the other one. So we'll study two TCP implementation, the TCP Tahoe and the TCP Reno later. And then now we can estimate the roughly the TCP rate as the congestion window divided by RTT. Congestion window tells you like how many bytes are sent in that particular let's say time, and RTT is like the rough estimate of how many, I mean, how long does it take to send the segments and then receive an acknowledgement. So this is just rough estimate of TCP rate. Okay, now let's talk about the TCP slow start. This is well, normally this is used at the beginning of the TCP connections, and in some TCP implementation, this can also be used when it detect. I mean, when the congestion is detected. Okay, so but by default, when the connection begins, the TCP, the sender, will start with sending one segment, and then increase exponentially. So, for example, one segment at the beginning, and then if there is no packet loss, then send the two segments, and then four segments, and so on and so forth. So it can, I mean, after 4, 8 segments, and then 16, and so on. But then, I mean, this is like this. We start slow, only one, but then ramps up exponentially fast. Okay, but then there will be some problems because if we send too many segments afterwards, then this will be, I mean, there will be more probability of congestion. So there should be a limit when we have to stop the exponential increase. Right? So after some point that we define as the slow start threshold, okay, or SS thresh. This is a short form of slow start threshold. The congestion window will increase linearly. Okay, so from exponential to linear. So after the SS thresh. And why this is so? Because this is like try to avoid the congestion. Okay, so because in this figure, after 8 segments, then in the next transmission round, it should go up to 16 segments, or congestion window will go up to 16, which is too big. Okay, so the implementation is this could be the SS stress will be the variable, and on loss event, SS stress is set to half of the congestion window just before the loss event. Now we'll see how this is implemented in different, let's say, TCP implementation. Well, if you talk about the SS stress, this will be the same. Like for example, in this case, we are sending. First, we start with the slow start from 1 until 4. So we are at SS state, slow start, and then from 4 to 8, we are in the congestion avoidance state, right? And then when the congestion window equals 12, or when we send 12 segments, the sender experience packet loss. So in the next transmission round, if we are using the TCP Tahoe, the congestion window will start again from 1, and then start with slow start again. Okay, so and the SS stress, or slow start threshold, will be half of the last congestion window here. So the last congestion window equals 12, then the SS stress will be 6, right? Okay, so the SS stress after the last after the loss event is 6, half of the congestion windows. Okay, so well, this is not the correct illustration of TCP Reno and TCP Tahoe, but anyway, this is just to show how the SS stress will be changed after the loss event. We'll use the correct illustration in the next slide. Okay, so from the previous illustrations, there are different mechanisms when the packet loss or segment loss is detected, and how the TCP implementation reacts to this packet loss. Okay, so for the loss indicated by timeout, the congestion window is set to 1 MSS. 1 MSS means that starts again from one segment, okay, to be sent, and then when the window grows exponentially as in slow start until it reaches the SS stress, and then grows linearly. Okay, so it means that we are entering the congestion avoidance state. Okay, so this is in Tahoe and in the TCP Reno. Okay, so both. But then for TCP Tahoe, it's always set to 1. In both cases, either for time, the loss indicated by timeout, or if the loss is indicated by 3 duplicate ACK. Okay, so now especially for TCP Reno, if the packet loss is indicated by the 3 duplicate ACK, the next congestion window will be cut into half. Okay, but then actually there is an addition here. It will be added to 3. Okay, well, we'll see in the next slides when we are talking about the TCP Reno implementation. Okay, so first let's have a look at the FSM, or final state machine of TCP Tahoe. So in the TCP Tahoe, there are only 2 states, which are slow start and the congestion avoidance state. Okay, and then okay, so in the beginning, when the sender starts sending a segment to the receiver, it will start to the slow start state. Okay, and then it grows exponentially. All right. So anytime the ACK arrives, the congestion window is it grows. Actually, this is if you read this, it looks as if it grows linearly, but then this is calculated by one, I mean, for each segment, or for each segment sense. So for example, if the current segment is only one, then one segment plus one. Okay, so 1 plus 1 equals 2, and then the next segment, then there will be 2, then each segment will be added to 1. So one segment add to 1, 3, and then the other one add to 1, and it equals 4. Okay, and then the next time, for each of the segment is added by 1, so then the next one will be 8. So basically this shows the exponential growth. Okay, so this is the slow start. Okay, until we reach the SS threshold, the slow start threshold, then we'll enter the congestion avoidance state, and then in this state, the congestion window will grow linearly, and again, it seems as if it is, I mean, it's not linear. It's like there's an upper bound, but actually this is linear. So we only increase one segment, okay, in the next after every transmission round. All right. So if there is any packet loss detected, whether we are in the slow start at the moment, or we are in the congestion avoidance, then we always go back to the slow start state. And whether the packet loss is detected by a timeout or by the triple duplicate X. Okay, now so let's see the graph, like how this congestion window evolves in the TCP Tahoe. So we start from a slow start mode, or slow start state, 1, and then increase to 1, 2, 4, 8, and then there is timeout detected here, and then it will start again to from 1, the congestion window equals to 1, and then we grow. I mean, and then the last congestion window before the packet loss is detected, or the loss event is detected, it was 8. So the next SS threshold is equals to 4. And the initial SS stress equals to 16, by the way. So actually it can grow up to 16 if there is no congestion. If there is no congestion, which is indicated by the timeout or by the triple duplicate act. Okay, so the next transmission round after 3, then we grow slow start again from 1 to 4, and then after 4, congestion window equals to 4, then we start entering the congestion awareness state. Okay, and then we start to grow linearly until we get the packet loss, and eventually it is detected by triple duplicate act. Right. So again, in TCP Tahoe, whether it is indicated by timeout or triple duplicate act, we'll start again from 1. Okay, but then there is a difference in the SS threshold value. This time, because the last congestion window was 12, then in the next transmission round, the SS will be half of 12, which is 6. So in this case, the slow start will grow from 1, 2, 4, and then up to 6, because the SS threshold is 6. We cannot go up to 8. So after 6, after this, then the congestion window will start to grow in linear fashion. Okay, so I think this is quite clear for the TCP Tahoe, and then we'll see TCP Reno in the next slide. Okay, so the main difference in TCP Reno is that now we have one more state, which is called the fast recovery state. Okay, so in the fast recovery state, so before that, there is also a difference in how the TCP Tahoe reacts when it detects the packet loss. So when the packet loss is detected by a timeout, it always goes to the slow start state. So in whether we are in the slow start state now or in the fast recovery, if there is timeout, then we always go to the slow start, and when we are in the congestion avoidance, we always go to the slow start again. Okay, now if the packet loss is detected by the triple duplicate ACK, then we go to the fast recovery stage. Okay, so whether we are in the slow start, okay, or we are in the congestion avoidance stage, if there is still duplicate ACK, then we always go to the fast recovery state. And now, when we are in the fast recovery state, there are two states in which we can go out from the state. Okay. 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 Of course, like if there is timeout, then we should go to the slow start. But then aside from that, if there is there is a duplicate act arrive. This duplicate act arrive means that so for example, we are sending 8 segments at the same time, and then there is we detect that uh, uh, there is a packet loss from these 8 segments. We don't know which segment which is lost. Okay, and then we go to this fast recovery state. Okay, from whatever the question window is. Then in the next transmission, we should receive the same duplicate. We will receive the duplicate act. Whether it is it's not the new acknowledgement, but it could be like something that was still within the lost packet before. So we are still in this fast recovery state until we receive the new acknowledgement. New acknowledgement means that let's say before we send 8, and then we will the next transmission round will send 7. Okay, and then eventually we finish all this the previous segment that was lost, and then we'll receive the new acknowledgement. So we'll enter the condition of readiness stage. And now there is also difference in the new condition window after we get the 3 duplicate acts. Okay, so when we receive the triple duplicate act, the SS stress is the same. It is still half of the condition window in the previous time. When we get the packet loss event. Okay, but then the new condition window will be the SS stress plus 3. So, for example, if the last packet loss happens when the condition window equals to 8, then the new SS stress will be 4, and the new condition window will be 4 plus 3, then it will be 7. So now let's see the implementation or how the TCP Reno evolves in the graph. Okay, so in the first, actually this is the same. We are using the same event as the previous TCP tachograph, but the only difference is when there is a 3 duplicate acts detected at this 13 RTT or transmission round. Okay, so we start with the slow start mode, and then there's timeout, so we go back to condition window equals to 1, and then again we are entering the slow start mode or slow start state up until we are reaching the condition window equals to 4, or when we reach the SS fast. Then we enter the condition avoidance state, and then when we receive 3 duplicate act here, and let's say 13, then we go to the fast recovery state. Okay, and in the fast recovery state, the new SS stress is the same as before. It is the half of the last condition window, which is 12. Okay, and then the new condition window will be the SS stress 6 plus 3, which is 9. All right, so then we are when we are still receiving the duplicate act or the acknowledgement from the old, let's say the old segments, we are still in the fast recovery state, and the fast recovery state it also looks like the slow start, which is growing exponentially, but it's not starting from 1, but from the point when the condition window starts like this from 9, then grows exponential 1 and then 2 until we receive the new acknowledgement. Okay, so when we receive the new acknowledgement, then we enter the congestion avoidance stage, which is starting from the SS stress again. Okay, the congestion window equals to SS stress. Okay, so and then the congestion window will grow exponentially from this point. Okay, so this is the actually this is the main goal of this video, but then I'm just going to give you another flavor of TCP implementation. There's also something called TCP cubic. So basically, this TCP cubic is using cubic or equations or x to the power of 3. If this is a axis, x-axis for example, then normally cubic equation will look like this, right? So this we are using this as the what is called the like the in this case before it's like the SS stress, but we just saying that this is the W max, the maximum sending rate before the question was detected. Okay, so the intuition of this is we are trying to achieve higher throughput than the normal or classic TCP with the AIMD, because if we are looking at this graph, I mean, if we just apply the calculus, how to call, I mean, the area under this graph is larger, or there is more than the area under this graph in the red graph compared to the blue graph, right? So we are actually trying to achieve more throughput than the classic AIMD TCP. And the intuition is we try to have a larger increase when we are further away from K. So let's say K is the W max, and we can set the value of K. And when we reach or closer to K, then we are increasing slowly. Okay. So this is the TCP cubic. We'll try to let's say get the more throughput in compared to the AIMD TCP, and this is default in the most Linux implementations. And lastly, in this video, we will try to discuss about the explicit congestion notification. This is also called the network assisted congestion that we have briefly discussed in the previous video. So what's happened is, let's say a source is sending to destination, and we have we're not discussing this at the moment because this is in the IP layer or network layer. There is additional field in the IP layer called ECN, congestion notification field or flag, and then it was 10, and then after let's say arriving at this router, and this router it experienced there is congestion in this router, and then the router adds this value 11, meaning that there is congestion in this network. So when the packet or the segment arrives at the destination, the receiver, when it sends the acknowledgement to the source, then it will add this bit ECE in the TCP header, notifying the sender that okay, there is a congestion in the network. So I think that's it for the TCP congestion control, and we'll finish at this in this video for chapter 3, and then we'll see you again in the next video when we discuss about the network layer data plane. So see you again in the next video and in the new chapter.